Thank you to everybody who's joined us to our next Learn with BT webinar, IPTV addressing multicast versus unicast. My name is Liz Rapley. I'm the Director of Marketing, and I will be moderating this, but I'm really going to just turn it over to Wes in a few seconds. Couple housekeeping rules. At the bottom of your screen, you should see a Q&A button and a chat button. When you have a question, feel free to utilize those buttons, and we will address all the questions at the end of the presentation. So without further ado, I'm going to turn it over to Wes Waite, who is our instructor extraordinaire. Thanks, Wes.
Thanks, Liz. Hi, everyone. Thanks for joining us on this episode of Learning with Blonder Tongue. And today we're going to talk about IPTV addressing. How do we address things to send video across an IP and Internet Protocol network? We're going to talk about multicast versus unicast addressing. How do we do it? What does it mean? Discuss talk about some of the address ranges that are standardized across the industry. I'm going to touch on IGMP, which is one of the protocols that's necessary to enable video to get across our network without flooding the network. And then finally, MPTS versus SPTS, another great set of acronyms there for us. Multi-program transport stream versus single program transport stream. What does that mean? What does it do for us? And the like. So I will start out with discussing, let's see here, why is this not advancing? There we go. So IP addresses. Everybody should be familiar with what an IP address is. It's the address, like everybody has a home address, a home number to their address. It's an address assigned to a device on a network, so that when that device wants to talk across the network, we can figure out where that information is supposed to go and where it's coming from. So IANA, the Internet Assigned Number Authority, is the main branch, the main authority that assigns all the public IP addresses. So when we're going out to the world, when we go hit google.com or blondertongue.com or whatever, those public addresses that are accessible to pretty much anyone, those addresses are assigned by the Internet Assigned Numbers Authority. There's two types of IP address structures in use that we primarily see. IP version 4, which is something like 192.168.10.100. That's a 32-bit address, has 4 octets. The octets have values from 0 to 9 digits. So that can give us a total, so we can go from 0 to 255 for each group, each octet. So with that, there can be a total of 4.3 billion addresses given out from 0.0.0.0.0 through 255.255.255.255. So the public address section of the IPv4 range, the public addresses, all of those have been allocated out. They were exhausted in 2011. So since then, the domain has been using IPv6 version 6 addressing. It's a much larger address. It has, you can see the example there. I'm not going to read it all out, but it contains 128 bits instead of 32. So there's 8 groups of hextets, what they call hextets because they're hexadecimal numbers, which includes 0 through 9 and A through F in the address. So that, with that 128 bits, ranging from, all zeros through all Fs, winds up producing 3.4 times 10 to the 38th. So 3, 4, and then 38 zeros after it, which comes out to about 100 decillion addresses. Just to give you an idea of how many addresses that is, the Earth's surface is roughly 7.9 times 10 to the 17th square inches. So we can put roughly 2 addresses in each square inch of the Earth's surface and still have a little bit left over. So we're hoping not to run out of those addresses anytime soon. But for IP television, IP video is primarily run on a closed network, so we primarily run IPv4 on that private network. So that's what we'll be discussing today. Just wanted to mention the IPv6 and its use. So there's another there's another group called the INTERNIC, the Network Information Center, that has reserved specific private IP address ranges. So there's Class A, which range from 10.0.0.0 through 10.255.255.255. We call that a /8 address, and I'll explain what the /8, /12, /16 means in a minute here. And then Class B is a 172 range, Class C is a 192 range. And again, I'll explain the slashes here in a minute when we talk about subnets. So with IPv4 addressing, again, it's 32 bits. Each byte or 8-bit segment is divided by a period and expressed as a number from 0 through 255. IPv4 addresses, the 4 groups of numbers, consists of 2 parts. And if we look down a couple lines there, there's an example, the 168.212.226 in red and then .204 in blue. So the 2 parts of that address, one identifies the network, and that example 168.212.226 is the network part of that address. And then the other part of the address identifies the node or the host. So in this example, .204 is the host. So this device lives on a network. The entire network is addressed as 168.212.226. This particular device has an address of .204 as it lives on that network. The class of the address determines which part of the address, which of those 4 groups of numbers, belongs to the network and which part belongs to the node. All the nodes on a given network share the same network prefix but must have a unique host number. Otherwise, there would be data collisions and all sorts of unruly things would happen. So again, here we have the example, 168.212.226.204. /24. /24 tells us the subnet mask. And the subnet mask can be identified in other ways, like 255.255.255.0 is a Class C address, or a Class C subnet, excuse me. But basically, that subnet tells us what part of this address, the 168.212, what part of it is for the network and what part of it is for the node or the host. So consider each octet of the address as 8 weighted binary numbers. So we're going to break down this 168, this first group in the address here. And you can see here, I've made 8 different choices here and weighted them from the right as 1, 2, 4, 8, all the way up through 128. That's basically how the binary system works. So we're saying we have 1 worth 128, 1 worth 32, and 1 worth 8 value. So if we add up 128, 32, and 8, we wind up with the number 168. So the 168 number translates to binary as 10101 If we were to write it out instead of regular number, write it out as binary, that's how it would write out. So in this example, the red number is total 168, which is the first octet of the IP address shown above. So that's how it would break down into binary. Here are some other examples of binary numbers, starting with 1. Again, we have the weighting across the top of this chart, and then for a value of 1, it's just 1 in the ones column, and then everything else would be zeros all the way down through 255, which is the sum of all of the different values. Okay, some of the common ones: 16, 127, 172, 192. That's how they would look in the binary format. Now the subnet mask, I've mentioned already, the /24, /16, what have you. The subnet mask tells us which part of the address belongs to the network and which part belongs to the node or the host. Most common subnet mask or CIDR classless interdomain routing is 255.255.255.0 or a /24. So if we break that out, 255.255.255.0, we break that down into binary. It looks like this: 8 ones, dot 8 ones, dot 8 ones, dot 8 zeros. And if you count up the ones, it equals 24. So that's the slash, because each group is 8 bits, so 8 times 3 is 24. So that's how we get the /24 designation. That's just a shorthand. A lot of people will say the subnet is 255.255.255.0. More people who work with internet systems on a daily basis use the shorthand of /24 network. So this subnet mask tells us the first 3 octets belong to the network. The last octet is the host. Just it's the same example as the previous slide: 168.212.226, that's the network. .204 is the host for that device on the network. So Class A subnet, Class A just has the first group, the first octet is 255, so it's a /8. Class B subnet is 255.255.0.0, so it's a /16. And a Class C I've already covered, 255.0, so it's a /24. Now those are the 3 primary classes. There is also what we call a classless, the CIDR, the classless interdomain routing can be between a class A, B, and C. So like a /26 would wind up with a fewer number of hosts than a class C. So it has 62 hosts. A /20 would have fewer hosts than a class C. And then there is a website available, www.subnet-calculator.com, that will help you further understand subnets. You can plug in an IP address and its subnet, and it will tell you the starting address and the ending address of that range, what's the broadcast address for that range, and everything else. Okay, but that's subnet mask. Now the classes themselves. A Class A IP address, the first bit of the first octet is always going to be a 0. So the range is from 1.x.x.x to 126.x.x.x. 127, the whole 127 address range is reserved for a loopback address. The default subnet for Class A is 255.0.0.0, which gives us 126 different available networks in that range, okay, from 1 to 126. Within each network, each of these Class A networks has 16.7 million hosts available per network. So in a Class A, again, the first octet is for the network. And in a Class A, the second, third, and fourth octets are for the hosts. So if we take the number of hosts, which is 24, right? There's 8, 8, and 8 in the groups, the octets there. So 24, so raise 2 to the 24th power, and then subtract 2 from that total. One is for the network number and one is for the broadcast address. And you wind up with that 16,777,214 available hosts for each one of those networks. For a Class B address, the first 2 digits in the first octet are always going to be a 1 and then a 0. So that gives us the range of 128.x.x.x through 191.x.x.x. That gives us the default subnet of 255.255.0.0. And that will provide us with 16,384 networks. Each of those networks can have up to 65,534 hosts per network. So now we're working with 2 to the 16th number of hosts. So it's the network and minus the network and the broadcast gives us the 65,000 hosts available. Okay. Our Class C, we usually work with a Class B, a 172 address, or a Class C, a 192 address, typically in our day-to-day work on private networks. In a Class C, the first 3 bits of the first octet are always going to be 110, which gives us a range of 192 through 223. Again, our subnet is 255.255.255.0, which provides us with 2,097,152 different networks. Each of those networks can have up to 254 hosts on each network. So like a 192.16.0 network would have 1 through 254 hosts on it. Class D is our multicast range. Class D addressing, the first 4 bits in the first octet always have 1110 as their starting binary number, which means that the range for that is 224.0.0.0 through 239.255.255.255. So the start of 224 up through the end of 239. The 224 range has certain addresses assigned to it dedicated to router and switch management. So typically it is a relatively large range. We're not going to use all of that range for multicasting. I have never seen a system use anywhere near that amount of addressing for multicasting through a system. So typically we're just going to avoid the 224 addressing. Start at 225 to avoid any interference with router and switch management. In the Class D range, there is no subnet mask. They don't identify a subnet mask. But when we do address it, when we talk about coming from a transcoder with an IP signal output, and we talk about receiving that signal with a VLC media player or an IP set-top box, we need to identify which port is used along with the IP address. So for an example, we would call it IP address 225.10.10.10 would be the IP stream that our IPTV signal is on, and that's also using port 50,000 in this example. And Class E is an experimental range of IP addresses. from 240 all the way up through the end of 255. I have no further knowledge on what exactly it's being experimented with, but I do know that there is no subnet mask for that range as well. Now, public IP addresses are provided by the internet service provider. So if Bonner Tongue wants to provide a public IP address for one of our pieces of equipment so that one of our remote sales guys can access it or a customer can access it, we would get a public IP address from our internet service provider, and then assign it to a machine so that people outside our network can access it. And again, that's the internet service provider gives it to us, but that database, the listing of public addresses is maintained by IANA. The private addresses used on our closed networks, again, are the 10 range, the 172 range, the 192 range. Those are used within our network, within our company, to talk to each other, to talk to our servers, things like that. But then we have to shift through our end router to get out to the world. We have to do other things to allow our computer to talk to the outside world. But those are our internal IP addresses. The multicast IP addresses used on a private closed networks, again, 224.0.0.0 through 239.255.255.255. And again, the 224 range, the beginning of the 224 range, is used for routing protocols and switching. So it's strongly recommended to avoid these addresses. I mean, you could start at 224.0.1. something. But just as a matter of course, I typically start at 225 whenever I start addressing things, just to avoid that whole range and not run into any issues. And again, we also have to indicate the port number to use when we're multicasting IP video. So we could potentially have multiple devices sending out IP television signals on the same IP address with different port numbers involved. That could be a possibility. That could get confusing, but it is a possibility. So multicast, I've talked about multicast a little bit here. Multicast, there's the range again. So multicasting IP signals is where we take signals from one source, like a encoder, something that takes in an HDMI signal or a component level video signal and makes it an IP stream. Now we want to send this IP stream across our networks to multiple users, multiple receivers. And the easiest way to do that is with multicast, because multicast allows this one source to send it out to multiple receivers, but we're not sending out multiple copies of the packet. We're just routing it through our switches and routers. We're just routing it only to those people who request it. So we don't overload our network with, flood our network with just a whole bunch of this IP video stream. So again, multicast sends one copy of the data packets out. It gets routed only to those receivers requesting it. Both the source and the receiver point to the same multicast IP address. So 225.168.2.20 is in the multicast range. So I would set my destination IP on my encoder or transcoder, whatever the source device is. I set the destination as 225.168.2.20, as well as setting an appropriate port number, such as 50,000 or 5,000. And for my receivers, whether it be VLC or an IP set-top box or another transcoding type device that receives IP, I set that receives IP address as 225.168.2.20, same IP address, okay, and the same port number. And so think of this as kind of a virtual IP address kind of floating out on the network that both the source points the IP stream to, and then anybody on the network who wants to view a copy of that also points to that same IP address. For Unicast IP streams, so that's uni meaning one, Unicast IP streams is where the source delivers the IP stream only to one receiver. Only one device on the network can see this stream. So in the Unicast mode, if you will, the source device will point to the receiver's IP address, and the receiver points to the source IP address. So for example, 192.168.2.30 and then 2.50 are the addresses of, one of them is the address of the source, one of them is the address of the receiver that wants to see that source signal. So they point to each other's IP address, and those two are the only ones sharing that IP video signal. Okay, I mentioned IGMP. IGMP stands for Internet Group Multicast Protocol. It's the standard of the protocol used to allow multicasting to occur across switches and routers on a network and minimize the data traffic flow so that we don't overload switches, overload the network. So right now, IGMP v3, version 3 is the latest. It claims it's backwards compatible to version 2 and version 1 components. I have not personally worked with a system that has both version 3 and version 2 or version 1 switches on it, but I am told from others who have that it can be a little finicky at best. So it's always best to have the same version hardware on your network if you can. IGMP version 1 was the original protocol, became the internet standard. Version 2 added low leave latency, so it reduces the time that a router learns that there's nobody downstream of them attached to that network segment that wants to receive part of this multicast group. And version 3 adds features for source filtering, so devices on a network segment don't get multicast packets from a source when there's no receivers interested in getting that data. Basically, version 1, version 2, version 3, just increasing ways to connect and disconnect from a multicast group faster. Here's an overview of the feature summaries for each of the different versions. We will have a copy of this presentation available in the next day or so up on our website, as well as a video, a copy of this recorded presentation. So you'll be able to review this. So switch settings for multicast. There's 3 key settings that we need on all of our switches in a network to be able to properly distribute a multicast signal, again, without flooding or overloading our network. I'm going to start with IGMP, again, Internet Group Multicast Protocol, snooping querier enabled. So it's used to support a layer 2, most switches are layer 2, multicast domain of switches in the absence of a router. For example, where multicast content is provided by a local server, but the router on that network doesn't support multicast. So this snooping querier kind of oversees all of the multicast stuff that's going on the network and keeps track of it, okay? It keeps track of who's doing what and keeps track of the data flow. So you need at least one switch per network enabled with the snooping querier to have a happy network, to have a good, robust network, IP network with multicast on it. The next setting is IGMP snooping enabled. Every switch on the network should have snooping enabled. This allows the switch to detect the messages exchanged between the router or the switch, the query switch, and the multicast hosts attached to the interfaces. So then when somebody comes online and says, I want to join this 225.10.10.10 and start watching whatever, HGTV or History Network, whatever is on that IP stream, it gets this request and sends it to the querier or the router that's running things and maintains a table that forwards the V4 multicast traffic to the ports that need to receive them. So it keeps track of who's where and who is requesting to join a specific multicast group, so it knows where to route the data. And then IP multicasting enabled on every switch. Again, as you can see there, it's an efficient way to use network resources for bandwidth-intensive services such as audio and video. Well, we're talking about IP video here. IP multicast routing enables a host, the source, to send packets to a group, the receivers, anywhere within the network by using a special form of IP address called IP multicast group. So the sending host inserts the multicast group address in the destination field, and IP multicast routers, so with multicast enabled, routers and multi-layer switches forward the incoming packets to all interfaces that lead to members of the group, the multicast group. Any host, regardless of whether it's a member of a group, can send to a group. Only the members of a group receive the message. So snooping and IP multicasting enabled on every switch is kind of the traffic cops that help direct traffic through the switches, right? And then the snooping querier enabled, again, need at least one of them on the network to oversee everything and make sure everything is playing nicely together and not flooding the network. Okay. And now we have finally the MPTS versus SPTS streams. MPTS is a multiple program transport stream. So multiple programs, meaning think of like a QAM channel. If you're familiar with the RF QAM channels, there's multiple programs on each QAM carrier to maximize the use of that bandwidth space. Well, in an MPTS IP stream, it's the same thing. There's multiple programs on one IP address and port, similar to putting multiple programs on one QAM channel. Primarily, MPTS is used for transporting multiple IP streams from one location to another. So if you've got two different head ends and you're sending local content or whatever, you have antennas only at one location, so you're sending local content over to the other head end. You would do that with MPTS just to minimize the number of streams you have to send across. It can be used to deliver programming to the customer. The VLC media player will show multiple program transport streams and allow you to pick which one to view. Okay, but now think about this. I've got my VLC media player open on my laptop and I'm watching Discovery Channel. Well, I'm receiving Discovery Channel, History Channel, and whatever else, 2 or 3 other programs all at once. So I'm receiving the bandwidth of 4 or 5 different programs, but I'm only watching one of them. So it's using up much more bandwidth on our system, it's not the most efficient way to send signal out to our customers. So typically in a system, we don't want to run MPTS, multiple program transport streams across to our customers. We want to run SPTS, single program transport streams. Each program gets assigned an IP address and a port. And so now if I'm tuning into Discovery Channel, I'm only receiving Discovery Channel. I'm not receiving the History Channel and whatever the other channels are. You know, only that program data is sent, so it provides much smaller bandwidth across my IP network. Now, a lot of devices, if you're setting them up to transport QAM and IP at the same time, such as maybe one of our, say, our AQT8 transcoder, or the HDE8C QAM IP, or the DIN series of encoder that has multiple sources coming into it and multiple programs going out of it. If you set it up for both IP and QAM, you're typically going to set it up to maximize bandwidth on the QAM side, i.e. putting multiple programs on each QAM carrier, so you maximize the use of the QAM carriers. That will duplicate over to the IP side. So if you have two channels output with 4 programs each, you're going to also have 2 IP streams with 4 programs each. Some of the newer equipment, like the next gen gateway, does not do that. You can individually control putting MPTS on QAM channels and putting SPTS on IP streams. So that's a good thing. That helps maximize the bandwidth use on QAM and minimize the amount of bandwidth use on IP. Okay. And with that, the bulk of today's presentation is done. And I'm going to kick it back to Liz to see if there are any questions that have come across.
Well, no, there have been no questions that have come up throughout this webinar, but one's just there. How many people use V6?
Well, I myself prefer a V8. No, I'm just kidding. So V6, version 6, IP version 6, you're going to start seeing it more and more in the public domain. I do not know of anybody using IPv6 in the private domain as of yet, but V6 is used, from what I hear. Like, I've talked to our IT guy for our company, and the addresses going from our routers out to the world are addressed as V6. But internally, all our stuff is IPv4. So I think as far as that, it's really only going to be what you see going out into the public domain that you're going to see V6 for a while anyway.
Well, I think you were very thorough on this presentation, because there are no other questions. I haven't heard
either that or the information was so engaging that I put everybody to sleep.
Well, we hope that's not
one or the other. Oh, somebody here. Oh,
here we go. Okay. You see these questions then?
Yeah, so I'll start at the top. When streaming internal video feeds, have you seen success over Wi-Fi? That's a whole different animal. So when you're streaming over Wi-Fi or trying to stream to a web browser or something like that, there's a specific, this IP video that our encoders and most encoders generate are designed for hardwire networks. They're not designed for Wi-Fi. The Wi-Fi requires, because again, it's going over open space, hence the name wireless, internet. So it needs other checks and balances also, in addition to the standard IP that goes across a wired network. So is there success over Wi-Fi? Yes, but it's a different format of signal. It is not this standard IP video. Okay. Is there another IGMP version beyond 3? Not that I know about at this time. Luis asks about what about VLANs? Well, that can be a whole nother hour-long subject. You can run VLANs to separate your control ports away from your data ports, but I'm not going to dig too deep into VLANs today. And Jorge asks, what about the recording? Yes, this is being recorded and will be posted on the website probably up by tomorrow afternoon. My static address.
We'll also be sending
Liz.
out an email with the recording for you as well.
Okay. Okay. My static address has both V6 and V4. Yes, a lot of them do. Nice presentation. Thank you. Not true. I'm not sure what that refers to. I have made multicast work over Wi-Fi. The only thing I had to do was turn on multicast forwarding on the access points. Otherwise, the exact same stream. Okay. I personally have not had much success with standard multicasting over Wi-Fi, but I was using an older wireless router, so that may be part of the issue. I've been asked the best way to get a camera feed to remote TVs in our lobby. Was thinking Wi-Fi wouldn't be very reliable. Well, it's as reliable as the connection between the router and the receiving device, the televisions in the lobby. So if you can count on that, then it should be okay. And thanks for the info today. You are welcome anytime.
We really appreciate your time learning with BT today, and stay tuned to our website and your email notifications, because we'll be doing another webinar in the near future.
Thank you all.
Thank you all. Have a great day.